A hydraulic press used to forge aircraft components can exert a force of 50,000 tons. The pump driving it fits inside a room. The operator controls it with a lever requiring minimal physical effort. Between the lever and the 50,000-ton force is a system of pipes, valves, and cylinders filled with oil, and the physics that connects them is one of the most useful principles in all of engineering. Most people have a general sense that hydraulics involves pumping fluid to move things. What is less understood is why the force multiplication is so extreme. Why a pump producing modest pressure can drive a cylinder capable of moving loads that no mechanical system could approach. The answer lies not in any exotic property of hydraulic fluid, but in a geometric relationship. It follows directly from the incompressibility of liquids and the mathematics of pressure acting on area. Pascal's law states that pressure applied to an enclosed fluid is transmitted equally in all directions throughout that fluid. This is the foundational principle. When a pump applies pressure to a hydraulic circuit, that pressure exists equally at every point, in every pipe, every valve cavity, every cylinder chamber connected to the pressurized side. The pressure does not diminish with distance. It does not weaken at the far end of a long pipe. It is the same at the pump outlet as it is at the actuator, subject only to friction losses in the pipework. Force is pressure multiplied by area. A pressure of 300 bar, typical of an industrial system applied to a small piston. A cross-sectional area of 1 square centimeter produces a force of 300 kilograms. Applied to a piston with an area of 100 square centimeters, the same pressure produces a force of 30 metric tons. Applied to a piston of 1,000 square centimeters, it produces 300 metric tons. The pressure is identical in all cases. The force is determined entirely by the area of the surface. This is the mechanism of hydraulic force multiplication. The pump generates pressure. The cylinder converts that pressure into force by presenting a large area to the pressurized fluid. The ratio of the cylinder area to the pump piston area is the mechanical advantage of the system. Unlike a lever or a gear train, this can be achieved without any direct mechanical connection between the input and output. Pressure is the intermediary, and it travels through pipes. The law of conservation of energy imposes the constraint that makes this multiplication physically consistent. If a small pump piston moves a large distance to produce a small volume of fluid, energy is conserved, and that fluid drives a large cylinder piston through a proportionally smaller distance, energy is conserved. The small force applied over a large displacement at the pump equals the large force applied over a small displacement at the cylinder. A cylinder with 100 times the area of the pump piston moves 100 times less distance for each pump stroke. The force is multiplied by 100. The distance is divided by 100. The energy, force multiplied by distance, is the same at both ends, minus losses to friction and fluid heating. This energy conservation relationship means that hydraulic force multiplication is not free. It comes at the cost of displacement. A 50,000-ton press moves slowly, because the volume of fluid required to move a massive piston, even a small distance, must be supplied. It must be supplied by a pump that is delivering that volume at high pressure, stroke by stroke. The press is powerful, but not fast. Speed and force are the fundamental trade-off in any hydraulic system, just as they are in any mechanical power transmission system. And the hydraulic system's advantage is that this trade-off can be adjusted continuously and precisely through valve control. The hydraulic pump is the energy source of the system. It does not create pressure directly. It creates flow. The pressure in the system is determined by the resistance to that flow. If the pump delivers fluid into a circuit with no load, the fluid flows easily. Pressure is low and force is low. As the actuator encounters resistance, as it lifts a load or pushes against a structure, the resistance to flow increases. Pressure rises to the level required to overcome that resistance. The pump continues to deliver the same flow rate but at higher pressure. This self-regulating relationship between load, pressure, and flow is one of the reasons hydraulic systems are so practical. A hydraulic excavator arm encountering harder rock automatically develops higher pressure without any operator intervention. The system responds to load. An electric motor driving a mechanical system must be sized for the peak load. A hydraulic system sized for peak pressure can deliver that pressure only when needed, at lower energy consumption during lighter loads. The relief valve is the safety device that defines the maximum operating pressure of the system. It is a spring-loaded valve set to open at a specific pressure, diverting flow back to the reservoir when system pressure reaches the set point. Without a relief valve, a blocked actuator, a cylinder that cannot move because the load has exceeded its capacity, would cause pressure to rise, without limit until a component failed. The relief valve prevents this by providing a controlled pressure ceiling. Every hydraulic system has one, and its setting is the fundamental safety parameter that governs the maximum force every actuator can exert. Control valves, directional control valves, flow control valves, pressure-reducing valves allow the operator to direct the hydraulic power correctly. A directional control valve connects the pump output to one side of a cylinder and the other side to the return line. This drives the cylinder in one direction. Reversing the valve reverses the connections and the cylinder direction. Proportional valves, whose opening varies continuously with the control signal, allow precise control of flow rate and therefore actuator speed. Servo valves, high-precision proportional valves used in aerospace, can position actuators to within micrometers using feedback control systems. They compare actual position to commanded position and adjust valve opening to minimize the error. The hydraulic fluid itself is not a passive medium. It is a precision engineering material whose properties affect performance and longevity. Viscosity, the fluid's resistance to flow, determines how easily it moves and how effectively it lubricates the moving parts. Too low a viscosity, and the fluid leaks past seals and between close-fitting surfaces, reducing efficiency and allowing contamination. Too high a viscosity and flow resistance increases, causing significant pressure drops and potentially leading to pump cavitation. This creates vapor bubbles in the low-pressure zone that collapse violently when they reach high pressure, damaging pump components. Contamination is the primary cause of hydraulic system failures. Particles of metal circulate and cause abrasive wear on precision surfaces. Water contamination, from condensation or external ingress, reduces viscosity, promotes corrosion, and can cause vapor lock. Air contamination, from suction leaks or improper filling, causes spongy, inconsistent actuator response because air is compressible. Filtration systems, typically multiple filter elements at different points, continuously remove particulate contamination. System cleanliness is measured in ISO 4406 cleanliness codes. Precision servo systems may require cleanliness levels that demand particle counts in the single digits per milliliter of fluid. Heat is a byproduct of every hydraulic system in operation. Every inefficiency in the pump, every pressure drop across a valve, every throttling of flow through a restriction converts hydraulic energy into heat in the fluid. In a continuously operating system, this heat accumulates and raises fluid temperature. Elevated temperature reduces viscosity and increases leakage. It accelerates oxidative degradation of the fluid and reduces seal life. Heat exchangers, either air-cooled radiators or water-cooled heat exchangers, remove this heat from the fluid to maintain operating temperature. Thermal management is a routine design consideration for any hydraulic system that operates continuously under load. The aircraft hydraulic system illustrates the extreme end of hydraulic engineering requirements. A commercial airliner typically has 3 independent hydraulic systems, each operating at pressures of 200 to 350 bar, each supplying flight control surfaces, landing gear, brakes, and thrust reversers. The independence of the 3 systems ensures that a single failure, a pipe fracture or pump failure, does not disable all functions simultaneously. Flight control surfaces that are supplied by all three systems can continue to function on any one of them. The hydraulic fluid used in aircraft systems, typically phosphate ester-based, is chosen for its fire resistance. This is critical where a fluid leak near a hot engine or brake could ignite. The landing gear extension and retraction cycle on a large aircraft illustrates the speed force trade-off in practice. The gear must retract quickly after takeoff. Aerodynamic drag from extended gear is significant. But the retraction force required is modest. The gear must extend and lock before landing and withstand impact loads of touchdown, forces far exceeding the hydraulic extension force. The hydraulic system supplies the force to move the gear and engage the locking mechanism. Structural locks carry the landing loads independently. If hydraulic pressure is lost, the locks hold the gear in position, and a separate gravity extension system provides a backup. So why can hydraulic systems lift thousands of tons with a single pump? Because pressure is force per unit area. Pressure transmitted through an enclosed fluid acts equally on every surface it contacts. A pump delivers that pressure to every cylinder. A cylinder with a large piston area converts that pressure into a proportionally large force. The pump does not need to be large. The force multiplication ratio is determined entirely by the ratio of cylinder area to pump piston area. The pump generates pressure. Pascal's law distributes it. Area converts it to force. And conservation of energy ensures that the multiplication of force comes at the cost of speed, a trade-off used for over a century. To learn more about how aircraft flight control systems respond to hydraulic failure and how crews manage the transition, watch my other video.